Welcome to the Boston Echo Board's review course. In this section, we will be discussing various transducer resolutions, specifically spatial and temporal resolution. We will also be discussing aspects of transducer design, impulse formation, and propagation to the tissues that impacts these resolutions. Specifically, we'll be discussing pulse propagation and errant behavior of impulses through propagation that lead to degradation of the resolutions and generation of visual artifacts. Thank you and enjoy the section. The resolution is defined as the ability to resolve position in space or time accurately. Spatial resolution is the ability to image and resolve position in space. And one of the most important resolutions is axial resolution. It is defined as the ability of the system to display closely spaced two structures which are parallel to the ultrasound beam. As has been discussed in the transducer design and the impact of the backing material, this is determined by the spatial pulse length, that is the source and the medium at the same time, which means the source determines the length of the spatial pulse of the pulse length, and the medium, as the pulse goes deeper and deeper into the tissues, the spatial pulse length increases, and therefore the spatial resolution or the axial portion of the spatial resolution is deteriorated. Shorter duration pulses increase axial resolution, that is, improve the ability to resolve the position in space when they are lying in parallel to the ultrasound beam. This is also called as longitudinal, radial, or depth resolution. It cannot be adjusted for a specific transducer because spatial pulse length cannot be changed. It is fixed for a specific transducer. The typical value of an axial resolution of an ultrasound transducer is 0.1 to 1.0 millimeters of mercury. So axial resolution and spatial pulse length are closely related. As you can see up top, the green is a longer spatial pulse length. There are these two reflectors that are closely spaced to each other, and the distance between the two of them is shorter than the actual spatial pulse length. So erroneously, they are reflected and seen on the image of the ultrasound beam as a single reflector because the distance between these two transducers is less than the spatial pulse length. As opposed to the transducer at the bottom, the spatial pulse length is red, and the distance between the two reflectors is more than the length of the pulse, and therefore they are accurately reproduced as two separate reflectors on the image display. Therefore, axial resolution is spatial pulse length divided by 2. The important aspects of spatial pulse length and axial resolution to be remembered at all times are that axial resolution improves with shorter pulse length, axial resolution improves with shorter pulse duration, and a higher frequency transducer that has a shorter spatial pulse length has a higher axial resolution because of its shorter wavelength. Fewer cycles per pulse, which is less ringing and therefore improves axial resolution. And the lower the numerical value of the axial resolution, the better it is, which means going from 1 to 0.1 implies that the axial resolution has improved about 10 times. The lateral resolution is the ability to distinctly identify two structures when they are perpendicular to the sound beam's axis. As is obvious, as you can see from the graphic, this is determined by the width of the ultrasound beam. And as the beam diameter changes with depth, hence lateral resolution changes with depth, which means it is not as good at the start of the beam, it is best as the focal point, and then further deteriorates as you go into further depth from the point of the focal beam. It is also called as azimuthal, transverse, or angular resolution. Narrower beams obviously have better lateral resolution, that the ability to identify the position in space from side to side is better. And it is also determined in units of distance. Therefore, as you can see, analogous to the axial resolution, when two objects are closer than the beam width, they are seen as a single reflector. As up top over here, the two reflectors closer to the beam, the distance between them is less than the width of the beam, and hence they're seen as a single reflector. However, the focal point, the width of the beam is less than the distance between two objects, and they are reproduced accurately as two separate objects. And as the beam goes further deeper into the tissues, you can see that the beam diverges, becomes broader, and therefore the lateral resolution gets worse as you go into the far zone of the ultrasound beam. Quite obvious as it is seen from this focal point that lateral resolution is best at the focal point. So higher frequency transducers improves axial resolution by shorter pulses. Higher frequency transducers improves lateral resolution because beam is narrow and diverges less, and axial resolution is better than lateral resolution for any given transducer. So for any given transducer, axial resolution is always better than the lateral resolution. The next is the elevational resolution. So normally, as we all know, that the transducers are disc-shaped transducers, and they are assumed to have no height or thickness to their beam. So beam however, has some elevational resolution as well, which means it is a certain amount of thickness of ultrasound beam that is present in these when it propagates through the tissues. So the best elevational resolution is also at the narrowest point of the beam, and that is the focal point. So that's beam height determines the elevational resolution, and beam width determines the lateral resolution. So therefore, they are best both at the focal point. Normally, the assumption is that the ultrasound beam plane is a razor thin, but the beam certainly has an element of measurable thickness. So when the plane is thick, structures above and below the plane create reflections that appear within the image, which means the assumption is that the beam is razor thick. However, as it diverges, it incorporates height into its geometry as well. And therefore, structures which are above or below the beam are assumed to be within the scan plane's razor thinness level. So slice thickness is measured in a direction perpendicular to the image plane above or below the imaging plane. Therefore, if you're looking at the elevational resolution and transducer design, this consists of a rectangular shaped active elements placed side by side. That's the way the crystals are arranged. Phasing is the narrowing of beam from side to side, which is achieved by the arrangement of the crystals, arrangement of the focal point, arranging of curvatures, so that we have like we discussed in the transducer design and beam formation. All these factors turn to improve the lateral resolution. However, the thickness cannot be impacted as much because all these factors tend to reduce the width of the beam and not as much the elevation of the beam. So beam, as like its lateral dimension, thickens and widens progressively over distance, worsening the elevation resolution in the far field of the ultrasound beam. So as you can see from the graphic also, it's quite obvious that best lateral and elevation resolutions are achieved at the focal point. So now we get into the temporal resolution, which is the ability to identify position in time or the motion in time. This is also expressed as the frame rate of the ultrasound. So frame rate is the ability of the system to create numerous frames each second, which is an optional parameter of making a movie, which is creating frames one after the other. Units, it is reported in units of hertz per second, and it is determined by number one, a constant factor, that is the speed of sound in the medium, and number two is the depth of imaging. The speed of sound is assumed to be constant, that is 1540 meters per second, and that we will discuss certainly leads to sometimes generation of speed of sound artifact when this principle is violated. And clinically, however, with the speed of sound being constant, the imaging depth determines frame rate, which means the time to go to the reflector and come back determines how fast you can generate an image, which means the deeper the structure, the more time it takes for the sound to travel to the reflector and come back. Therefore, to sum it up, the temporal resolution is the ability to precisely position moving structures from instant to instant. This is accuracy in time. Temporal resolution is determined by frame rate, which is a higher frame rate, which implies a better temporal resolution. It is related to frame rate of its units or hertz per second. And temporal resolution also is a frame rate and time frame, which means the time it takes to make one frame, inversely related to image created in 1/10 of a second, which means the more scan lines you have, the more time you take to create an image, the more time it takes for the sound to come back from a reflector determines the temporal resolution, which means the higher the spatial resolution, the lower the temporal resolution, the higher the larger the depth also being an important determinant of how fast an image can be created. If anything, one of the things that makes absolutely crystal clear the difference between spatial resolution, as you can see in these two images, one on the left is a still high resolution photograph taken with a very high quality camera showing the fumes and almost droplets of Niagara Falls as the water falls over the cliff. On the right side, you see a motion, which means the 2-point discrimination of the spatial resolution in this movie may not be as great, but your ability to appreciate motion exists. So spatial resolution is improving spatial resolution is like taking a great picture, and improving temporal resolution implies taking adjustments to making a movie. So there's certain compromises and takeaways, and when you improve one and the other one deteriorates. So that's, you can't have everything at the same time. You can either have great temporal resolution or you can have a great spatial resolution. And in this context comes the concept of focusing that we had discussed in the arrangement of piezoelectric crystals, that it serves to narrow the beam as it travels through the tissues. So focusing improves lateral resolution by creating a narrower beam. There are multiple kind of foci that exist in a transducer design. Number one being external focusing that is performed with the lens. This is fixed and mechanical. This is the one that is present all the time. The second is the internal focusing that is performed with the introduction of a concavity or a curvature into the arrangement of the piezoelectric crystals. That can be a single curvature or multiple curvature existing to create multiple foci along the beam. And lastly is phased array focusing, which is performed electronically, which is adjustable. That's the one that when we adjust the focus on the machine, that can be controlled by the operator. So external focusing is focal depth and extent of focusing that cannot be changed. This was with the introduction of an acoustic lens in front of the piezoelectric crystals. That is, when they vibrate, there is a focusing of the beam as it travels away from the transducer, and the arc of the lens determines the extent of focusing. Quite obvious. The principles of optometry, which means the greater the curvature, the more it will be focused to the ultrasound transducer. The internal focusing consists of focal depth and extent of focusing that can also not be changed. It is the arc of the curved piezoelectric crystal that determines the extent of focusing, and it is the one that is used more commonly in the commercial ultrasound systems that we use. And the adjustable electronic focus of phased array transducer is the one that we can move by, is the operator adjusted focus, which means you can decide which would be the most narrowest portion of the beam when you're looking at the whole image, or that is the area or the region of interest that you want to concentrate on more, is the one that you want to have the focus adjusted to that depth, and that's electronic adjustable focusing. However, focusing is something that is not always or not entirely or universally does not universally improve the quality of the image. There are certain consequences. Number one, beam diameter narrows in the near field and the focal zone, which means it narrows pretty close, and the focus moves closer to the transducer when you narrow it. However, the beam widens even more beyond the focal zone if you move it too close to the ultrasound transducer, and therefore there is significant deterioration of lateral resolution in the far zone. And lastly, when we bring the focus closer to the transducer, we also narrow the total size of the focal zone. So this not that the image quality improves globally, it improves a whole lot close to the transducer, but there's significant more deterioration in the far zone than before we adjust the focus. So the resolutions are the questions they answer, and for any given transducer, axial is the best, second best is the lateral resolution, and third best is the elevation resolution. The questions they answer for axial, it is what is the minimum distance that two structures positioned front to back can be apart and still produce two distinct echoes on an ultrasound image. The lateral resolution is what is the minimum distance that two structures positioned side by side can be apart and still produce two distinct echoes on an ultrasound image. And elevation resolution is to answer the questions that are the reflections of the image created from structures directly in the image plane or from structures above or below the imaging plane. So now we come on to the generation of phased array transducers and generation of grading lobes, that is the deterioration of lateral resolution leading to artifactual creation of images it appears to be within the beam when they actually are not. So the grading lobes are off-axis beams, as you can see in this graphic. So as you see, they are outside the main beam, and therefore they lead to deterioration of the lateral resolution. However, the images that are created from these off-axis beams have a much lower amplitude than the actual reflectors that are present within the main beam. Let's just say this is a single element transducer. It produces side lobe by this mechanism. This is the beam. You can see the focal zone and two side lobes because of two ultrasound pulses that are going outside the main beam. The side lobes are located further than the focal zone. That's one of their characteristics. They're not at the point of the focal zone, and they are outside the main beam. As we go and we analyze it even more accurately, and they have a much lower amplitude. You can see this is the reflector. It is seen in the image display in the center. So as the beam will move from side to side as a result of phased array stuff, it will lead to generation of side lobes. So this reflector is interrogated by the side lobe beam as the beam sweeps over and an image is generated. And when it moves on the other side, the next side lobe beam interrogates it and generates an artifact that appears to be within the main beam. A question that is often asked is the difference between side lobe and a grading lobe artifact. Essentially, they are the same. They are just deterioration of lateral resolution. Side lobe artifacts are created by single element transducers, and grading lobes are created by array transducers. Side lobe are again off-axis beams that degrade lateral resolution. Grading lobes are also off-axis beams that degrade lateral resolution. They are both deterioration of lateral resolution. Side lobes are generated by single element transducers, and grading lobe by the phased array transducers. To review one more time, secondary beam detects the reflector. Secondary beam detects the reflector on either side of the main beam, leading to an image display demonstrating two reflectors on each side of the main reflector, which is seen as an image of much higher amplitude as opposed to the low amplitude image of the side lobes, which is a characteristic of them. And they're always located farther than the focal zone and are at the same level as that of the original reflector. The other thing that will be important to remember is that speed of sound not only impacts spatial temporal resolution, but it can also impact spatial resolution, and that's called a speed of sound artifact. For example, in the top image, speed of sound is traveling at the speed normal, which is 1540 meters per second, and hence the reflector is faithfully reclused. If the beam traveling slower than the speed of sound, the time it takes for the beam to come back is longer, and the machine assumes it to be even further deep than the original reflector and places the image of the reflector farther from the actual reflector. And if the beam travels faster than the actual speed of sound, that is the assumed one of 1540 meters per second, it takes less time to come back, and therefore the reflected image is reproduced and generated on the image display closer to the transducer than the actual reflector. So therefore, important to remember that the assumption of 1540 meters per second not only impacts the temporal resolution, but can also impact the spatial resolution. This brings us to the conclusion of generation of resolutions and a brief discussion on artifacts, which will be further discussed in more detail in the artifacts section of the physics workshop. Thank you.